The next coordinate system we're going to look at is our cylindrical coordinate system, or to be more specific, our circular cylindrical coordinates. And our three variables that we're going to use to define points and vectors in this system are rho, phi, and z, as we see in the upper right of the screen. As we've talked about before, this is convenient for problems with cylindrical symmetry, for example, transmission lines, and we'll see how the math works out for that a little later on. So let me go ahead and sort of post this pre-drawn coordinate system here. So notice I still have my axes labeled as x, y, and z. We have some point P that we want to define its location using our circular cylindrical coordinates. So I've sort of drawn in orange here some lines to sort of help us visualize these things. So kind of think of this as sort of just a wedge of cheese. So before I actually come up to this figure and label what our points are, let me define our rho, phi, and z explicitly down here below. So our rho is going to be the radius of a cylinder passing through point P. So radius of cylinder passing through our point. In this case, we're talking about point P. So if we come up here, we can see that the distance from our z-axis, sort of in the plane of P, is going to be our distance rho. So sort of along the top there, that's going to be our rho distance. So we can call this distance here, this would be our rho. Okay, so the next item is our phi. So our phi is our azimuthal angle, and so that's going to be measured from our x-axis and the xy plane. So measured from x-axis in our xy plane. So of course our xy plane is sort of everything down here without going up or down in z. And if we're measuring it from our x plane, what we're essentially doing then is we're going like this, and we say out to this point. So if we think of sort of this as being a square, like almost a sliding door and a revolving door that's going through, the angle to that sort of infinite plane or semi-infinite plane there would be our angle phi. So really not a semi-infinite plane, rather just a plane there, sorry. So that would be our angle phi to get to that point. So that would be our rho and our phi. And then finally, our z is the same as what we had in Cartesian. So let's just, for completeness, come down here and write same as our Cartesian or rectangular coordinates. So of course that just means from down here in our xy plane, we have to go up a height, in this case, of z. So in this case, I have this drawn for a point P that's in positive x, positive y, and positive z. But of course, we could define points in any point in space with our cylindrical coordinate system. So let's talk about the ranges for these three values, our rho, phi, and z. So our rho cannot be less than 0, but it can go all the way up to infinity. And so the way we get around that is, of course, we can go as far away as we want from our z-axis, but we can't go a negative direction. Instead, we just rotate the phi to a different angle, and then we have a positive distance from that axis. So our phi, that angle, of course, can go between 0 and 2 pi. So essentially one full revolution, so I only want to include one endpoint. So one full revolution around our z-axis. And then our z, just like before in Cartesian, can go from negative infinity to infinity. So now in terms of how do we represent a vector, it's essentially the same way with our, as we saw with our Cartesian. So we can use our angle brackets. The only difference now is we're going to have a rho component, a phi component, and a z component. Alternatively, we could also write our rho component times our unit vector in the rho direction, plus our phi component times our unit vector in the phi direction, plus our z component times the unit vector in the z direction. So I realized I've not defined what these unit vectors are. So at any point we could define these unit vectors. So let's come up here to our point P in our drawing. And let me do these in a new color. So let's do green. So our rho unit vector is going to be extending along this line rho here. So let's make this a little bolder too. So our row unit vector is going to be coming out in this direction. So this is going to be our u row. Again, just extending along that row line. Our z is going to be the same as Cartesian, so that's going up along that z line. So this is our u of z. And then finally our phi is going along this sort of phi direction here. So we have our phi unit vector in that direction. And so what we can notice, as advertised, all three of these are mutually perpendicular, as expected, because we have an orthogonal system. In terms of magnitude of our vector, so we can say magnitude of our vector A is of course just A without the arrow on top, and that's much the same as we saw before, so that's going to be each of the components squared, and then take the square root. So we have square root of our row component squared plus our phi component squared plus our z component squared. So that's how we're going to find our magnitude. Just briefly, we can also talk about our constant coordinate surfaces. So let me come down here and draw a new sort of axes. So constant coordinate surfaces. So same basic idea as with our Cartesian, but just a little bit different now that we have our row, our phi, and our z. So let me go ahead and draw our x, y, and z. So there's z, x, and y. So let's say we keep our row constant, so that first one. So maybe our row is set equal to something. So what we're going to end up with is a fixed distance from our z-axis. So that should be a cylinder that is centered on our z-axis, and so that extends in both directions. So it has all possible phi values, all possible z values. For z, of course, it's just going to be an infinite plane. For a constant phi value, we're going to have remember we talked about that sliding door. So it'd be like a door coming off of our z-axis in one direction, so we would call that a semi-infinite plane. But now if we talk about sort of two surfaces, so let's say we have z constant and rho constant. So if we have both of these constant, so we talked about our constant z surface is going to be a plane, and it's going to be sort of parallel to this xy plane, so we have something that looks like this. And again, that's kind of hard to interpret from my drawing, but hopefully you can kind of see what this is like in your head too. The intersection of our constant z plane, so here's our constant z, and this cylinder, or this hollow cylinder, is our constant rho, so the intersection of those two is going to be a circle. And so again, there's some more details in this in section 2.5 of the textbook, but the reason I bring this up now is it's going to be helpful later on when we're looking at solving certain problems and trying to fit problems into a certain coordinate system.